Here is the magnetic molasses lab report by me, Giannetto. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil. We want to model the magnet/tube interaction computationally using GlowScript, and then we compare our predictions with the data observed and what we saw in real life. We were trying to see what would happen in real life versus what happens in our computational model, and we're trying to explore Faraday's law and its effect in real life and how these interactions can affect each other. The core principles is that Faraday's law means that current will be induced in a loop by moving magnetic field. This magnetic field interacts with the magnetic field in the tube to create a force on the bar magnet. This force counters the force of gravity and slows down the magnet. The magnetic field interacting with each other creates a force. Basically, the movement of one magnetic field creates another magnetic field, which exhibits a force on the original magnet. Here's a preview of the velocity versus time graph that we used in our computational model. And also, here is a preview of our GlowScript code to show you what actually happened. The equations used to calculate magnetic field and other things in Faraday's law is the E field of a dipole, the B field of a dipole, the B field of a wire or a solenoid, the force on a wire creates due to a current, and then, of course, Faraday's law, the induced EMF due to change in flux. Data collection. Our prediction is that while the magnet is in the tube, it will fall slower than in free space due to induced current in the tube. Basically, that when we drop the magnet in the tube, it will fall slower than in free fall because there's induced current, which creates a magnetic field. In order to do this, we first decided on a set height to drop the magnet both in air and through the tube. We dropped the magnet and timed how long it was in the air. We did this multiple times to ensure accuracy. We double-checked this time with free fall calculations using just basic F equals mg, and then we dropped the magnet the same height but through the tube. We timed this as well, and then we repeated this experiment to ensure accuracy. What we observed is that while the magnet was in the tube, it fell slower than when the magnet fell in free space. This was not dependent on the orientation of the magnet either. Here are the videos. Obviously, on the left, it is free space. You can just see that again. And then on the right is through the tube. So here's some basic data collection that we did. We collected the length of the tube, which is 47 centimeters. And then it was 0.94 seconds for free fall outside the aluminum. This was average of a couple of test runs, and then 1.48 seconds inside the aluminum tube. GlowScript modeling. This is more complicated, one of the more complicated ones, but we create equations for induced EMF and force created by induced currents. We implemented formulas to calculate R variables, and then we modeled the magnetic molasses and the travel of the dipole magnet through the tube. Here's a look at the velocity time graph and the tube in time in seconds. It is much greater than what we observed, but this is due both to errors from the data we collected and also probably computational errors. Here is the rest of the code. Possible sources of errors is, of course, errors in timing and the calculations. So basically, the errors in which we stop and start the timer. Other errors include materials versus what we use in the GlowScript code, such as lengths and like how many loops there actually were. We were holding the magnet from slightly different heights, so we dropped it from slightly different heights each time, even though it was very similar. And then the dropping of the magnet was not perfectly into the tube every time. It could have hit the edge or something similar. Here's our discussion and conclusion. Induced currents can be created due to moving magnetic fields. This induced current creates a magnetic field of its own. The moving magnet and the coil will interact with each other, which basically means the moving magnetic, which creates an induced current, will interact with the magnetic field created by it, slowing it down and then reducing the change in flux. If the coil had near zero resistance, the currents would increase to create a greater magnetic field from the induced current that would further slow down the magnet. The slower magnet would then decrease the change in flux. If holes or slots were cut into the tube, there'd be fewer turns and thus smaller magnetic fields, and as thus the magnet would fall faster.